Okay, so we've been learning a lot about structures and understanding the structure that a covalent compound has. And the reason why we've been spending so much time on this is that structure determines functions. So the ways that molecules are put together determines the ways that those molecules are going to work. And we've been doing this to try and get to the point when we can understand why do materials behave the way that they do. So why is it that salt is able to dissolve in water and not able to dissolve in oil? Why don't oil and water mix? Why are metals able to conduct electricity? So like, why does stuff do what stuff does is ultimately the question that we're trying to answer right now. And to understand this, we now know the structure, and what we need to look at next is the forces that are governed by molecules. So when we have a molecule, we have to think about what force can it actually apply on other molecules? How well is it stuck together? How easily is it able to move around? Those things will actually determine the way that something works. The small scale forces that interact between two molecules will determine the way that an entire substance actually behaves. And so today that's what we're going to take a look at. And very first, what we need to understand is essentially the different types of bonds that we can deal with. And so what we're going to be looking at is the different types of compounds and their forces. Now, in like grade 10, you probably learned about different types of compounds, but those are held together using different intramolecular forces. Now, intra as a prefix actually just means inside. And so when we talk about an intramolecular force, we're talking about the force inside of a molecule. And if you think about what that force actually is, this is the type of bonding. And there are different types of bonding that are able to make compounds do different things. And hopefully what you learned when you were in grade 10 is probably that there were two kinds of bonds. In reality, there's actually more than two kinds, but we're going to talk about three in this lesson. So one of them is called ionic. An ionic bond is something you've probably seen before. It is a bond between a metal and non-metal. And an ionic bond is when you have a cation, so something that's positive, attracted to an anion, or something negative. So what happens in an ionic compound is you have some atom of some kind. I'm going to label this sodium. And then you have another atom that would be like a non-metal, or maybe a polyatomic ion. I'm going to make this chlorine, because this is kind of a classic example of two metals, or of a metal and a non-metal, that are going to come together and be able to form an ionic compound. So what actually happens when these bond? Well, what happens is an electron goes from the sodium to the chlorine. Why is that? Well, let's think about Lewis structures for a second. Sodium has one valence electron. Chlorine has 7 valence electrons. What ends up happening here is chlorine is extremely electronegative. So chlorine is actually going to take this electron away, like actually rip it off of the sodium. And the sodium is okay with that because when the sodium gives away this electron, it actually makes it a little bit more stable. So what we end up doing is producing sodium that now has a full valence shell in its second orbital, like the second ring, right? If you think back to like your Lewis dot diagram or your Bohr model, you had your nucleus, you had your first orbital, you had your second orbital, and then sodium had one electron in its third orbital. This is the one up here that's going away, this valence electron. So that's the one that's actually disappearing. So now what's happening is you just have this full second valence shell. So I'm not going to draw any valence electrons. And what you have instead is something that's lost one electron and now become positive. The chlorine now has an extra electron, right? It picked up that electron from the sodium, so it now has a negative charge. So now you have this negative chlorine. And what happens when you have something positive and something negative is they attract, right? Positives and negatives attract. It's one of the laws of charge. In an actual ionic compound, you don't just have like one sodium sticking to one chlorine. Instead, what you have is like a sodium, and then it's going to be stuck to a chlorine. But there's also another chlorine nearby, and another chlorine nearby, and another chlorine nearby. And then there's sodium filling all those other gaps. And you end up getting really like a big lattice, a big crystal structure of these different atoms sticking together. And if you think about what's happening inside, each one of these green, each one of the chlorines is going to be negative. And like not a partial negative like we saw with polarity. We're talking like full negative, a full extra electron. The sodiums are all positive. And what ends up happening is all of these atoms are attracted to each other. Because there is so many positives, so many negatives, you end up getting this structure that has a huge amount of attraction. Everything is wanting to stick together. And this is what ends up happening inside of ionic compounds, is that ionic compounds form these big crystalline structures and are held together really, really tightly because there is a large amount of intramolecular force. So an ionic compound is held together very, very strongly. So a great example is think about salt. If you have never seen salt, go to the kitchen, look at some salt. What you're going to find is that salt, throw it on the stove and see if you can melt it. It doesn't melt till it's like a few hundred degrees. It is held together so tightly that it doesn't want to like pull apart, which means that ionic compounds tend to have very, very high like melting points, boiling points. They have all of these charged things in them, so they can actually conduct electricity through them. They tend to like break along certain lines. What ends up happening is if you fracture something like this, then it will actually just like open it up all the way. There's not a lot of flexibility or give here. So if you cause a split in part, that will just extend all the way through. And they tend to be very, like brittle because of that way that it's actually built. But this is an intramolecular force that determines the way that ionic compounds actually work. The other thing is, if you were to zoom in on salt, sodium chloride packs together like a little cube. I drew this in 2 dimensions, but this thing actually builds up in 3 dimensions. So what you would find is that these things pack together in a little cubic fashion. So you'd have like your sodium bonded to a chlorine, bonded to, like, there's another chlorine here, another sodium, but then we're going to make this 3-dimensional somehow. Okay. There's another sodium in the back, and then there's another chlorine back here. Okay. And so like this is connected to that. This is going to be connected to that. These are connected like this. And then extending backwards, you would also have like another chlorine back here. That's connecting here. And then you would even have like a little sodium in the back corner there. It's kind of tough to see. But you end up getting this cubic structure. And if you were to zoom in and look at actual salt under the microscope, might be a little tough. You probably don't have a microscope at home. What you would end up seeing is that salt actually forms little tiny cubes. Like salt grains are actually tiny little cubes. And if you let salt grow and crystallize, it forms like big cubes. This is where you get things like finishing salt if you're into cooking. You get like all sorts of structures, and basically it will always build up in some kind of cubic fashion. And it might even be like a cube stacked on a cube stacked on a cube to make like larger and larger structures. But this all has to do with the bonding, with the way that an ionic compound actually fits together. Different compounds fit in different ways, so they form different structures, and you get different crystalline shapes. So that's an ionic compound. Now, next we're going to focus on something that you probably didn't learn when you were in grade 10, and that is what's called a metallic bond. So think about the things that you know. You know about ionic compounds. You probably know about covalent compounds. Ionic compounds form crystal structures. So a lot of the things that you see that are like maybe powdered or crystals or things like that, I say like baking soda, baking powder, salt are really good examples of ionic things. You can also have things that are covalent that tend to be like gases, sometimes liquids, but like the air that you're breathing is covalent compounds. There's a lot of covalent compounds that exist. But the other thing is metals. Like metals, pure metals, are something that we see all the time. So how are they actually held together? Like how is it that gold is able to stick to gold? So what's actually going on there? Well, we didn't really go in depth about the ways that atoms actually look. But here's what I'm going to try and do, is try and explain this as best as I can using a really simple Bohr model. So let's think about some metallic nuclei. So like the nucleus of some metals. And I'll draw those in, this is purple. You probably can't tell because the lighting in this room, not exactly giving you some ideas about how this looks. But I'm going to draw my electrons in, let's go blue. Okay. Now, metals have actually quite a few orbitals. And this is going to look really messy because those orbitals overlap with each other. Because metals have such huge orbitals, their electrons end up overlapping. And this does something pretty amazing, is it makes what we would call a sea of electrons. It basically gives the electrons so much interconnected space that they're no longer actually bound to any one nucleus. So I apologize for taking so long here, but I really want to illustrate this point that when you have a metal look at how much of those orbitals actually overlap. So if I were to add, like, let's say there's an electron here, and there's electrons here, and all over the place, right? But these electrons, because they flow on these lines, they can actually move pretty much anywhere they wanted to, right? They can flow their way through a metal really, really easily. Electrons in a metallic bond are not stuck to any one nucleus. So this is what we call a sea of delocalized electrons. So what does that actually mean? Well, delocalized means not stuck to one nucleus. So in a metal, an electron is free to basically go to any nucleus that it wants to. And you have to remember that inside of a metal, there would be like millions upon millions upon millions of atoms, each with their own orbitals, each overlapping, and you end up having this huge, massive structure. So what does this actually do for a metal? Well, let's think about this. If your electron is able to flow freely and you apply some force to move those electrons, which we would call voltage, the electrons will actually just move all in one direction. And that is where we get electrical conductivity. In a metal, electrons are free to move, so they are able to conduct electricity through them. That's why all metals, by definition, have that ability. Metals also conduct heat really well. So let's think about what heat actually is inside of a substance. So heat in a substance is when one thing starts shaking. And when that thing starts shaking, it starts vibrating the things around it. So metals conduct heat because there's so much overlap that as soon as one of the nuclei starts shaking, its orbitals start shaking, which shakes the orbitals of the other substances, which shakes the nuclei of the other substances. And you get this big flow of vibration through a metal. And that's why metals can conduct heat. That's really handy if you're like cooking and you need a pan. That's why your pans are made out of metal, because they conduct heat so incredibly well. Metals also have some other really interesting abilities. So a metal doesn't melt very easily. It melts at a really high temperature. And they also have the ability to be flexible and to be flattened into sheets and stretched into wires and all sorts of things. So why is that? Well, it all comes back to orbital overlap. You see, in a metal, let's say you tried to like squish this metal or hit this metal. These nuclei may have lots of overlap, but they still have the ability to actually like slide and push some of these things out of the way because they're not held together really, really strongly by, say, like an ionic bond. All they're really held together by is just kind of overlapping with each other. So they're still able to have some flex and be able to move. And that allows us to change the shapes of metals quite easily with just hitting them or applying some force to them. But why don't they melt at lower temperatures if they can slide around so easily? Well, when you increase the heat, they start shaking, but they're still overlapping with so many other orbitals. And so that means you need a huge amount of energy to actually take this one nucleus and rip it totally free so that the nucleus can flow around in a liquid, right? That's what it means to be liquid, is to have atoms that can actually like slide and move past each other. And the electrons can move, but the nuclei can't move freely. They can be bent and moved out of shape with force, but it takes a lot of energy to actually allow them to break free from that big overlapping orbital structure. That's what makes metals really behave the way that they do. And those two intramolecular forces, ionic bonding and metallic bonding, determine really why those substances do what they do. Next video, what we're going to take a look at is covalent bonding. because covalent bonding is very different, and ultimately those compounds are governed by different forces that we call intermolecular. So make sure you check that out, and I'll take up any questions that you might have, but thanks for watching.